Okay, so today we'll be solving problem 1792 from the Hibbeler book. Take a second to read it for yourself and make sure that you know it's just about exactly what you want to do. In the meantime, I'll just mention that this problem is mostly it's mostly just about using the correct form of the equations of motion. The most that you'll have trouble with in this is just the moment part. Forces in the x direction, pretty easy. Forces in the y direction, pretty easy. Just make sure that you get the moment part right, and you'll pretty much get this problem right. Okay, so we're going to start out first by writing the free body diagram. The problem asks that you find the frictional force and the normal force at the bottom where it's touching. Now, one way to solve this problem would be using instant centers. I'm not going to be using that method, but, just if you wanted to, you could. But, yeah, so we only really have three forces here. Force due to the weight of the disc, then we have the frictional force at the bottom, and then we have the normal force that the weight exerts on the floor. Okay, so writing that out, we have f of x equals ma because in this problem the disk is moving. So normally for like a static problem, ma would be 0, but it's a dynamics problem, so ma actually has a value. So in this case, is f of x is in the negative direction, so it's negative f of x equals 10 times the acceleration due to gravity in the x direction, which we'll be discussing shortly. For the equations for the y direction, we have we have the weight, which is negative because it's going against it's pointing down. We have the normal force, which is pointing up, and we also which is going to be equal to the mass times the acceleration. Okay, and for our last one, we have the moment equation. Everybody knows how to do a moment and everything, but we'll be explaining a little more in detail in the next slide. Okay, so for the summation of moments, it's a little bit harder, it's a little bit more involved. As you can see by the black triangle, we kind of have a little bit of confusion going on around here. So the best way to solve this was to use the law of cosines to get that the length of the radius from the center to A. So we see that's 0.3477 meters. Now we use the law of sines to get the angle between RGA and RGL, which in this case is 25.2 degrees. Now we'll be using that later. There's also a distance on the semicircle that's highlighted in red. That distance is the distance from the center of gravity to A, and we'll be using that later. Oh, just one note, RGL, that's something, that formula that I use, that's something in the back of the book. Is on the back cover, it just tells you how to find the centroid of a semicircle. So on this slide, pretty much just put all those pieces together that we found in the last slide. What we want to focus on here is that we're not solving the moment equation about G. For this problem, we're going to solve it about A. What you want to remember here is that anytime you have something that's rotating, it's always the best thing to do is to go ahead and at least write out the fact that it has an angular acceleration, which you're going to multiply by its inertia, and it's also going to have a translational acceleration, which you'll multiply by mass. Even though not all the time will you use it, depending on where you're taking your moment about, but make sure that you at least always write it, because you don't want to forget it, because your equations, your answers and everything will be off. So using the angular acceleration equation, I think this was actually discussed in chapter 16, so this is a little bit of a review. So yeah, go ahead and plug in all your values. If you have trouble with anything about this equation, you may want to go back to chapter 12 and go ahead and look up of rectangular components. Just make sure that you can break those down in the I, J, and K directions, and make sure that you know how to do the cross product. Yes, that is a cross product. They're not really that hard. Just make sure that you know that you essentially know what you're doing. Something else that I'll point out in this is that first part where in the blue box it says AA, and in the equation underneath it, that AA is equal to 4 squared times 0.4j. Now that is actually the equation for acceleration. So just make sure that you know where that came from. After you solve that equation, you can break it down and solve the components for I and J, and once you do that, you should get an equation for each components of each of the x and y components of acceleration. So going back to the original moment equation where we have the AG and the AY, and we also have an alpha. If you go back to that equation and plug in those two, plug in the AG and the AY that you just found, you should get this last equation. It's very tedious, so make sure you don't mix up any numbers. Okay, so we're almost done here. Take the moment equation that you just found and the summation of the moments in the x direction and the summation of the moments in the y direction, and you have 3 equations and 3 unknowns. So you'll want to solve all 3 equations, and once you're done, you should get that the f of f is 20.11, the normal force is 91.32, and the angular acceleration is 13.85 radians per second. So yeah, the biggest thing about this problem is just the moments, making sure that you're using the correct moment equation, because it's very easy to just plug in a formula and get it wrong. And you have to understand these equations and the formulas and how to use them. So yeah, that's essentially the biggest thing to look out for. Everything else is what we've been doing this whole class period. So thank you for watching my video solution.